Well, thank you for getting ready to go and being all set in this class. We're going to get started with Chapter 1. It's a review of pre-calculus topics. And I start almost all of my lectures the same way. I'll start with a starter question. And I actually like to start off the entire calculus course by asking this question. And the question is, what do students struggle with most when trying to learn calculus? And I'll give you a second to think about that. The answer is they usually struggle with pre-calculus. That's usually what they struggle with. The ideas in calculus are really pretty easy to understand. It's a fairly basic concept. But what people struggle with is they can't do the algebra or the trigonometry to arrive at the right answer. So there might be a little bit of calculus in a problem to start with, and then a bunch of simplification with complex fractions and things like that, and people will forget what they need to do. So this is usually what people struggle with, and that's why it's important that you watch these videos, that you ask questions, and make sure that those diagnostic exams that are in the textbook that I've assigned, that you do those. The author thinks those are important. And then also I've gone through and picked some problems from Chapter 1 that I'd like you to do. So please be aware of that. It's not like we're just wasting our time here and spinning wheels. It's really important that you review this and get your questions answered so that when we do the calculus material, you can actually get through it. So we're going to start with a definition of a function. And this is a very informal definition. You'll find some mathematical purists that like to complicate things, but this is basically what a function is. It's a very consistent mathematical rule. It takes whatever you plug in, which is normally a number. Sometimes we'll plug in an expression. It does some math on it, and then it gives you an answer. And this is what we use a lot of times in math. We'll use functions. So the set of numbers that we plug into a function, they're called the domain. And the set of numbers that we get out, they're called the range. And since we usually plug in x's and get out y's, the domain is usually made up of x's, and the range is usually made up of y's, but that doesn't always have to be the case. Since we usually figure out what x we're going to plug in, we get to choose that. We call x the independent variable. And since y depends on x, we call y the dependent variable. And then we don't use this word very often, but I'd like to bring it up because it is used a fair amount. What we plug into a function a lot of times will be called an argument. So if I say what's the argument of the function, what we're talking about is what are we plugging into the function. So just some vocabulary there. And then occasionally we'll use function notation in pre-calculus. We use function notation all the time in calculus. Comes up all the time. So basically, instead of writing xy pairs all the time, we recognize that y is a function of x. The y coordinate is produced by plugging in a particular x coordinate. So y is equal to the function value at that particular x. So instead of writing y equals 2x plus 3, I could write f of x equals 2x plus 3. Now, instead of writing an xy pair, we're going to write an f of x pair. And the nice thing about function notation is when you look at it, we can look at this and we can tell, look, with the function f, we plugged in a 4 and we got out a 3, which means you can look at it and you can just see what the xy pair is. You plugged in a 4, you got out a 3, so the point that corresponds to that on the graph would be 4, 3. And then I'll remind you of a couple of other things about, about functions. The first one is functions must pass the, and I'll let you think about it for just a second, they must pass the vertical line test. They've got to pass the vertical line test. We don't like things like this. We wouldn't like a parabola that opens to the side, because if I go over here to 4, normally we just like one answer when we plug something into a function. Well, I'd get two answers out here. I'd get 4, 2 on a regular old sideways parabola, and then I'd get 4, -2. So that's no good. That doesn't pass the vertical line test. This is not a function. Okay, we don't like any ambiguity like that. Okay, and then I'll also remind you that there are a couple very common functions that have what I like to call domain issues. That means you can't just plug in anything you want. The first thing is division. You can't divide by 0. Okay, so cannot divide by 0. All right, so that's not allowed. The next thing is even roots. If you're taking an even root, you can't take the even root of a negative. So for example, you can't take the square root of a negative. That's not allowed. So you can't divide by 0. You can't take an even root of a negative. And the other function that comes up typically are logs. You can't take the log of, and I'll let you think of that one. You can't take the log of 0 or a negative. Neither one of those are okay. So you can't divide by 0, you can't take an even root of a negative, and you can't take the log of 0 or a negative. So keep those in mind because domain issues are a fairly big deal in calculus. So let's take a look at example number 1. On example number 1, we've got a function f of x that's radical 3x, square root of 3x. Function g of x is x squared minus 3. And it says, find the following and simplify, then state the domain of a and d. So just a and d. So you'll notice that on this one right here, we're supposed to take the function f and we're going to plug in the argument a plus 1. So wherever there's an x, we're going to put an a plus 1. So here's what we get. We get the square root of 3 times, well, it's normally 3 times x, but in place of x, we're going to put an a plus 3. So, an a plus 1. So we've got this expression right here. Now it would be a good idea to simplify this just a little bit. So let's write that as 3a plus 3, and that's what we get when we plug in an a plus 1 into that square root of 3x. Let's see what we get when we plug in an x plus h into this function. Well, this means wherever there's an x, we're going to put an x plus h. So it's normally best to plug in parentheses. So that's going to be x plus h quantity squared minus 1. Now, I'll call your attention to this because this is going to come up quite a bit, and typically students make mistakes with this. So sometimes people will just write, well, that's just going to be x squared plus h squared. That's what you get when you square x plus h, and that's not the case. Remember, what we get here is, this would be x plus h times x plus h. So I have to square that binomial. And if I square that binomial, I'm multiplying each one of these here with each one of those there. So that's going to give me x squared. This is going to give me xh. This is going to give me xh. And this is going to give me plus h squared and then minus that 1. So what I got here was x squared plus 2xh's plus h squared minus 1. And again, this is the term that people forget. They forget about that middle term that comes when we multiply the two of these and then they double up because they're exactly the same term. So this is the answer that we get from this expression right here when we plug it into the function g of x. And then this is a composite function. It asks us to find f of g of x. So that means we take the function g and we plug that into f. So the function f is this function right here. So it's a square root of 3 times something. Well, we normally plug in x. We put an x right here and an x right here. But what we're going to plug in here is g of x. And g of x is this expression. So that's going to be x squared minus 1. And again, it would be a good idea to clean this up just a tad. So let's write the square root of 3x squared minus 3. And we'll call that our answer for that composite function. And then this last one here. So for d, this again is a composite function. So we want to find g of f of x. So now we're going to take f of x and we're going to plug it into g of x. So what we get here is this. G is take whatever we're going to plug in and square it and then subtract 1. And let's think about what we're going to plug in. What we're going to plug in is the function f, which is the square root of 3x. So if I then go through and simplify, here's what I get. If I square a square root, those typically undo each other, right? So this is going to be 3x minus 1. So this is the composite function. Okay, now it did ask us to go back and figure out what the domain of a and d were. So let's take a look at this expression right here. So remember, this is one of those functions that has a domain issue. We can't take an even root of a negative. So whatever 3a plus 1 is, it better be not negative. Non-negative would mean greater than or equal to 0. It's got to be either positive, greater than 0, or equal to 0. So if we go ahead and whoops, that should be a 3. Sorry about that. Let's go ahead and solve this. So I'm going to move that to the other side. I do that by subtracting. Subtracting doesn't change the direction of the inequality. So this would be 3a is greater than negative 3. And then I'll divide both sides by 3. Now, dividing by 3 doesn't change the direction of the inequality. Remember, it's only multiplying or dividing by a negative as you solve an inequality that changes the direction of the inequality. So I get a is greater than or equal to negative 1. So that's the domain for a, and I'll put a box around that one right there. And then let's come and take a look at this one right here. Well, this one's kind of tricky because if you take a look at this, this would just be, and I'm going to write y equals, this would just be y equals 3x minus 1. Well, If we were to think about what that looks like, that's a line that crosses at -1 and has a slope of 3. So it would look like this. But keep in mind that this was made up of a composite function. So if we look back at the original functions, in fact, the one on the inside of the function, if you will, this is a square root function, and you can't take the square root of a negative. So whatever this is, whatever this 3x is, it better be greater than or equal to 0. Well, if I solve that for x, that means x has to be greater than or equal to 0. So the domain for this function right here is, and I'll let the computer catch up with me. Okay, so the domain is x has to be greater than or equal to 0. Now what that means is we don't get the entire line 3x minus 1, we just get this portion of it. And the interesting thing is we can check this on a calculator. Now your calculator is just a fancy computer, but it really doesn't know much other than what you put into it. So you'll notice that what I've got in here is not the 3x minus 1. I mean, we know what that line looks like. What I've got is the composite function. What happens when I take the square root function, plug it in and square it, and then subtract 1 from it? So the calculator is going to go through and it's going to plug numbers in. It's going to take the square root of that. So it knows it can't take the square root of a negative. So I'm going to hit zoom 4 and have the calculator graph. And you'll notice that it only graphs that one right there. So that is right, that the domain, okay, the x's that we can plug into this function are only from 0 to positive infinity. And I'll point that out right now. This is fine, this is inequality notation for the domain. The domain could also be written in interval notation, and that would be starting at 0 and stop at positive infinity. This one would be start at -1 and stop at positive infinity. It's always round around infinity, and then a square bracket represents that we can include that one. So let's take a look at example 2. Example 2 is another composite function. So we'll look at that one, and this is a little bit more complicated because these are both rational functions. So basically functions with fractions in them that have variables in the denominator. So this wants us to find f of g of x. And then stating the domain can be a little bit of a problem, but let's take a look at this. So I want to figure out what f of g of x is. So we're going to plug g into f. So f is this function right here. It's something minus 1, and then that same something plus 3. So what I'm plugging in there is I'm plugging in g of x. So I'm going to put a 1 over x right here, and I'm going to put a 1 over x right there. Now, I do need to go through and I need to simplify this. So let's take a look at how we do that. This is going to be 1 over x minus 1. And then this is going to be 1 over x plus 3. And in order to put those together, I need to get a common denominator. So to get a common denominator here, I'm going to multiply the top and bottom by x, and I'm going to do the same thing here. And if you remember from 1010, there's actually 2 different ways to simplify a complex fraction. I really like this method, but you're welcome to do it another way if you know what that is. This is going to give me one single fraction on the top of 1 minus x over x, and then the denominator is going to be 1 plus 3x over x. Well, with a complex fraction, remember we never divide fractions. We always flip the denominator over and we're going to multiply. So I'm going to multiply by an x on the top and then a 1 plus 3x on the bottom. That's going to allow me to cancel this factor of x with that factor of x. So I end up with 1 minus x on the top and 1 plus 3x on the bottom. And this right here is the final answer. This is what f of g of x is. This is what we get when we simplify. Now, it does say state what the domain is. Now, you need to be a little bit careful with this, and this is the way I like to do this. I like to tell students that if you're trying to find the domain of a composite function, look at the inside function. Look at the function that you start with. That's this one right here. Throw out anything that doesn't work right there. Well, if you look at this one, this is division. You can't divide by 0, so we know we can't use a 0. Then look at the end result and throw out anything else that comes up. So we know we can't use a 0, even though it looks like you ought to be able to plug in a 0. And then this denominator right here, 1 plus 3x, it better not equal 0. So let's see, if I solve this, I'm going to move that to the other side. I'm going to divide by 3. So the other one is -1/3. So the other number that it can't equal would be -1/3. So the domain on this one is everything except for the 2 of those. So you could just write that if you wanted to write -infinity to infinity, as long as x is not equal to 0 or negative 1/3. That would be kind of a little bit more complete answer, but this is fine right here. Now, it's pretty easy to see why negative 1/3 wouldn't work. It doesn't work in the end result here, okay? But again, sometimes it can be a struggle to see why 0 wouldn't work, because if you plug in a 0 here, you get 1 plus 0, so that looks like it's okay. But remember, everything starts with this inside function, so anything that's not okay to plug in to start with isn't going to be okay in the end result. And again, if you were to plug in this composite function right here in the calculator, it would show that there's a domain issue. The function value doesn't exist at 0 or at negative 1/3. Okay, now I'm going to show you the next problem because this textbook uses graphs quite a bit to describe things. And so this is important that you're able to do something like this. So you'll notice that we've got the graphs of f and g. Let me see what happened right here. I think we're still okay. So you'll notice that we've got the graphs of f is up here, the black one, and then g is this kind of reddish pinkish one right here. So what we want to do is we want to use the graphs of f and g to find the following values. So we want to find f of g of 5. So this means that we're going to plug in a 5 into g. So let's do that right here. I'm going to use the red. We're plugging in a 5 for x. So let's start right here, and I'm going to plug that in, and we're going to find out what g is. Now, if I plug in a 5, g of 5 is 1. So I'm going to follow that over here just to represent what we've got there. The function value, the y value that I get out is 1. Well, then I take that and I evaluate f at that particular function value. So I'm going to trade the y coordinate for an x coordinate. Instead of being the y that I get out, it's now the x that I plug in. And then I go up here and I'm not on g. I want to figure out what f of that value is, and it's right here. So the answer to this one is 6. Okay, let's do the same thing with this one, and I'm going to switch colors here. I'm going to start off with a 3, and we're going to plug that in. That's our x value, and we want to find the function value on f. So I'm going to go up here till I hit f. F is the black one, remember, so that one's right here. That looks like a 5. So the y value that I get out is a 5, and then I'm going to trade that for what I plug into g. So let's trace this down here. Okay, so I'm going to plug in a 5, and then I want g of that number right there. So I follow this up here, and I end up with a 1. So hopefully that makes sense as to how that works. It's kind of a nice graphical way of representing how we find composite functions. So we're going to talk about symmetry next. This is the bottom of the first page. Symmetry can often help us reduce the amount of work that's needed to solve a problem, or it can be helpful in just figuring out how a particular function works. And there are 3 different types of symmetry that we might be interested in, and we're going to take a look at those on the next page.